we're going to talk about some of the applications and models. We're going to talk about growth and decay, and then compound continuous interest. So we have a population growth model here of P of t equals P sub 0 e to the kt, where P sub 0 is our initial population, K is our growth rate, okay, and T is time in year, where K is going to be greater than 0. Okay? So our first example is in 2014 population. There's a population of 25.8 million with a 2.19 exponential growth. First, we want to find the equation. So we're going to go P of t equals P sub 0 is 25.8. So we're just going to keep it, and this will be in the millions. That's fine. E. Now I need to convert this to a decimal, 0.0219 t. Okay, so there's my information. And remember, T sub 0 is 14. So at 2014, we're at 0. So we're going to subtract from there to find the next piece. So the population in 2018. So how many years is there between 2018 and 2014? So what we're going to do is find that difference. So we're going to go 4 years. So in 4 years, we have 25.8 e to the 0.0219 times 4. We're going to plug this all into our calculator here. So I have 25.8 times e to the 0.0219 times 4. And that's going to give me a new population of 28.2 million people, okay? So in 4 years, they're going to have increased almost 3 million people, about 2.5 million. The other place where we see this a lot, and we use this a lot, is compounded continuous interest. So now in your book, they put it as P of t equals P sub 0 e to the kt. They use that k because they're always talking about the growth rate as being k. So that way when we're talking about doubling time and half-life and stuff like that, we're using that same variable. Most books will have this as kind of like PERT. Principal e to the rate times time, same thing. Okay? So suppose $2,000 is invested at rate k, compounded continuously, and grows to $2,504.65 in 5 years. What is the rate? Well, the first thing is we're going to have to set this up into this. So I know that this is my P of t. So now I have 2504.65 equals 2,000 e to the k times 5, right? So the first thing I'm going to need to do is divide everything by 2,000. Okay, this just gives me a decimal, so 2504.65 divided by 2,000. This is going to be 1.252325 equals e to the 5k. Well, the way I get rid of e is I take the natural log. So I'm going to have the natural log of both sides. The natural log of 1.252325 equals 5k. And then I divide by 5. Okay, so I'm going to take the natural log, natural log of 1.25, and then I'm going to divide that by 5, and I get 0.045 equals k, or 4.5%. Now here's my interest rate. Okay. So now I can plug this in. So now I know P of t equals 2,000 e to the 0.045 t. And now it says, what is it going to be after 10 years? So now I'm going to plug 10 into this. Okay? And now I'm going to just kind of work this with my calculator. Let's see here. E to the 0.045 times 10. And I get, after 10 years, we're going to have a value of 3,136.62. Okay, Compound interest is a great thing. You can just leave it in there and let it go and kind of go on forever. So there is a comparison between doubling time and the half-life and stuff like that. So growth rate and doubling time. So K is my growth rate, T is my time to double. So KT equals the natural log of 2, or K equals the natural log of 2 over T, or T equals the natural log of 2 over K. Okay? Same thing for half-life. Okay? So the only difference is my growth rate's going to be negative there. Okay? So our example here is going to be population in area is doubling every 37.7 years. What is the growth rate? So I'm looking for the growth rate. So I would have K equals the natural log of 2 over 37.7. Plug this into my calculator. So I have natural log of 2 divided by 37.7. And my growth rate is 0.01839 or 1.839%. There's my growth rate. Decay rate and half-life. So the decay half-life is a very interesting thing. You talk a lot about that in chemistry and physics, but it's that same formula. So KT equals natural log of 2, or K equals the natural log of 2 over T, or T equals the natural log of 2 over K. You're going to use those same formulas to find half-life or decay rate. The last thing we're going to talk about is if I want to convert from base B to base E, if I have B to the x, how do I get that to be E to the x? Well, B to the x is going to equal E to the x natural log of B. So if I have 8 to the x, this is going to give me E to the x times the natural log of 8. Okay, natural log of 8 is just a number. Okay, lots of applications for exponential functions. We use them all the time, and log functions, natural log.